Start with something familiar. A crystal is ordered and periodic. Shift it by the right distance, and the pattern repeats exactly. That repeating symmetry is why crystals are mathematically simple and physically powerful. In the 1980s, physicists discovered quasicrystals. These are ordered but not periodic. They are not random at all, yet no finite shift makes the pattern repeat. The structure follows strict rules, produces sharp diffraction peaks, and has long-range order, but it never loops. One way to build such a pattern is to start with a perfectly regular lattice in higher dimensions, slice it at an irrational angle, and project that slice down. The higher dimensional order survives, but repetition is lost. Now, shift from materials to spacetime. In Einstein's relativity, spacetime is smooth and continuous. But many physicists suspect that at extremely small scales, that smooth picture breaks down. Spacetime may be discrete, made of fundamental events rather than a continuum. Here's the problem. If you discretize spacetime using a regular grid, you pick out a preferred rest frame. That breaks Lorentz symmetry, the principle that the laws of physics look the same to all inertial observers. Lorentz symmetry is tested with extreme precision, so breaking it is not an option. There is a known workaround. Randomness. If spacetime points are sprinkled randomly, no direction or frame is preferred on average. This preserves Lorentz symmetry statistically, but the structure is essentially noise. There is no built-in order. This tension sets the stage. Can spacetime be discrete without being random and ordered without selecting a preferred frame? That is where spacetime quasicrystals come in. A spacetime quasicrystal is a speculative proposal in which spacetime itself is a discrete set of events arranged with quasicrystal-like order. The pattern is deterministic and highly structured, but non-periodic. There is no repeating four-dimensional unit cell, so no obvious rest frame is singled out. Importantly, this is not a quasicrystal sitting inside spacetime. The spacetime events themselves form the quasicrystallite pattern. Recent theoretical work has shown that such point sets can be constructed directly in Minkowski spacetime in a way compatible with Lorentz symmetry. The construction again borrows the cut and project idea, but adapted to a Lorentzian geometry instead of ordinary Euclidean space. This does not prove spacetime works this way, but it shows the idea is mathematically possible. Why do physicists care? First, quantum gravity. Discreteness could regulate the violent infinities that appear when quantum mechanics and gravity are combined. Spacetime quasicrystals offer a form of structured discreteness that avoids both rigid lattices and pure randomness. Second, symmetry. They provide a potential route to discretizing spacetime without immediately violating Lorentz symmetry, which is the central obstacle for most discrete models. Third, new degrees of freedom. Ordinary quasicrystals support special collective modes called phasons tied to their aperiodic order. A spacetime analog could introduce new fields or excitations with subtle gravitational or cosmological effects. Fourth, cosmology. If spacetime has an ordered but non-repeating microstructure, it could leave distinctive, non-random correlation patterns in the early universe, different from both smooth continua and stochastic discreteness. What spacetime quasicrystals are not is just as important. They are not the same as time quasicrystals realized in laboratory systems. They are not experimentally confirmed, and they are not a complete theory of gravity. At present, they are better thought of as a candidate microscopic geometry, not a finished physical model. There is also no evidence yet. Any test would be indirect, involving tiny propagation effects, extra weakly coupled modes, or subtle cosmological signatures. The constraints are severe, and many versions of the idea may already be ruled out. So the bottom line is this. Spacetime quasicrystals are a speculative attempt to combine three things that rarely coexist: discreteness, order, and Lorentz symmetry. Physicists care not because the idea is established, but because it opens a new geometric way of thinking about one of the deepest open questions in physics: what spacetime is made of at the smallest scales.